Hello everyone. In this particular lecture we are going to discuss basically different types of digital elevation models and their issues associated with them, and also we will see the different types of resolutions which are considered in remote sensing and GIS. Especially we will be focusing more on spatial resolution. What basically spatial resolution means and when it varies, how and the appearance in the data or if of a digital elevation model may vary. As we know that a digital elevation model is a raster representation, it is a surface and it is in grid form, so that each cell represents a value, and as you know that in raster each cell or pixel can have only one single attribute. Here if we consider as a elevation value, then we call as a digital elevation model, but sometime people also use a term digital terrain model, and basically it is mathematical surface which might be created through interpolations or might be digital elevation model might come from remote sensing data analysis as well. Depending on the size of the cell, the resolution is decided, and this like here that in this particular example a cell has been further divided. So, here you are having the smallest unit here, and it will have its own value, and therefore, if you are having the entire grid having this much size of cell, then it is relatively is going to be the higher spatial resolution. But the same time the data volume, smaller the cells, the data volume would be very high relative to the if cell size remain like this. So, this one has to keep in mind. Now, spatial resolution, as we can understand, that is a measure of how closely pixels or cells can be resolved in an image or a grid is called spatial resolution, and it depends on the properties of the system that creating the image or your grid. If you are creating a surface using point data through interpolation techniques, at that stage we can decide in mapping units what is the resolution, at what resolution I want the surface. But in case of satellite data, during only design process it can be decided. Before I go further details in this, I would like to bring 2-3 things about digital elevation models particularly, because nowadays many free digital elevation models of different resolution derived from variety of methods are available freely on net for entire globe. The earlier and the earlier one, the most popular one was there, which is called United States Geological Survey (DEM), and initially it was available at 1 kilometer resolution. Now, this DEM was created using topo sheets, contour lines. Those contour lines were interpolated and surface were created. So, we can write here say interpolation. The method here is interpolation, the source data was topo sheets. Then a DEM which is again is quite popular, which is called SRTM DEM. SRTM stands for Subtle Radar Topographic Mission. Basically this was about 20 days mission of NASA, which uses the SAR interferometry technique of remote sensing and covered the entire globe, almost 90% of the globe except the polar regions, and created DEMs for the entire globe at 2 different resolutions. One is 90 meter and one at 30 meter. And so, here the method which we can write here is INSAR, SAR interferometry, in short we say INSAR. Now, the third type of digital elevation models which are available now and for the entire globe is called ESTER DEM or ESTER GDM, It is available at 30-meter resolution. When I say 30-meter resolution, I mean a spatial resolution, 30-meter spatial resolution, and the technique has been used is stereo pair. This technique can also be employed with the Indian remote sensing satellite like Cartosat and others. And you can create a digital elevation model of 4-meter spatial resolution. The technique would remain same. These are freely available. This you have to create. This is at cost. So these models are available. Digital elevation model. Their genesis are different, and their spatial resolutions are different. Now basically depends for what purpose you want to have a digital elevation model. If you are going to cover a large area, then relatively coarser spatial resolution digital elevation model will be sufficient for you. But if you are working for a small area, then one should go for higher spatial resolution DM, because the area of coverage is going to be less. As we know that higher spatial resolution will bring the clarity in your image. If we go for a relatively coarser resolution, two examples are given here, that a 30 kilometer cells like this or 110 kilometer cells, hardly anything can be seen. So this is depending on what problems you are working. But sometimes, like here the example is shown for climate models, because if for climatic studies or climate change studies, you might be covering the entire globe, and therefore going for say 30 meter or 1 kilometer resolution, it would be too much data to handle, and you may not achieve whatever you wanted to achieve through those climate change models. So you may go for relatively coarser resolution data, and therefore for what one has to know the purpose, and accordingly different spatial resolution models should be used. This example also is that when you are having the grid 100 by 100 grid for the same area, then this character R is appearing much sharper, and when this number of cells reduces for the same area, here like 5 by 5, nothing is visible here, and in between it improves as you go for a smaller size cells. DM, as discussed already, that is a digital elevation model, and each cell is a raster and a grid, and each cell of the grid is representing a elevation. Now the elevation value can come from variety of techniques which we have discussed, and basically it represents this is a surface, so represents the spatial distribution of elevation values above some arbitrary datum in the landscape. Generally we represent above mean sea level, and DM is a surface which can represent maybe groundwater, maybe chemical qualities of soils, water, whatever the phenomena which varies with distances can be represented using the same concept. We may not call as a digital elevation model, we may call as a simple surface. One of the examples of digital elevation model is given here, and this elevation model is having elevation ranges between 95 meter to 3070 meter, and you can then assign some colors or shades of gray, like here for highest value white color, for lowest value dark color, and rest of the values are in between. So when you are having this kind of variations of a terrain in a small area, you can see even the valleys and stream network which are visible quite easily here. Now sources of DM, which I have some of the freely available DMs which I have already mentioned here, that you can digitize data, or you can arrange digital topo sheets, take the contour lines, convert them to point, and using interpolation in GIS you can create the surface. Through interpolations you can create the DM, or download the free DMs of USGS DM, SRTM 1 kilometer as well as 90 meter, and there are certain problems with free DMs like USGS DMs for Indian tiles. It is having seams because as mentioned here that these have been used while using the interpolations. So the maps might be having a different projections or might be surveyed at different times, maybe having different density of contours or intervals of contours, and therefore when you join two topo sheets together you might get that seams. So this is the problem of the USGS DM of 1 kilometer resolution of Indian tiles. 90-meter resolution had a lot of voids for the hilly terrains of India, specifically because of Himalayan terrain. And as you know that for SRTM, which is subtle radar topographic mission, using INSAR technique, 2 resolution DMs were created. Also 1 kilometer, 90 meter and later on 30 meter was also, now it is available. So this is based on the SAR technique, and as you know Himalaya is having large area is under snow and ice, and therefore whenever you find this kind of problem in radar because of different dielectric constant and in radar remote sensing you do not get the desired data, and therefore when the DM was created it developed voids. Little later we will see how voids can be removed, but anyway for hilly terrains of India and the voids were there even at 90 meter resolution, 1 kilometer resolution and those other resolutions as well. These voids can be substituted, the values of these voids can be substituted with lower resolution or some other, and like spatial resolutions of this one having a 1 kilometer, say example of USGS DM, whereas for the vertical resolution the USGS DM having the 100 meter. That is the least count or accuracy, vertical accuracy of a DM. So depending on the DM, different DMs, they are having different spatial as well as vertical resolution. Now this is void and the seam problem with the USGS. This is the example of Himachal Pradesh. As you can see that there might be one topo sheet here and another topo sheet might be here, and therefore the seam is very obvious and it is clearly visible here. So this might be having a high density or close interval contours, whereas it might be having a large interval contours, and therefore the seams are visible in 1 kilometer resolution of DM of Himachal Pradesh or many parts of India, especially of hilly terrain. Now the problem about the voids. So in 90 meter resolution DM it had the voids, and voids gets the no data value in GIS, as no data value was assigned here is minus 32768, that is the no data value, not the 0 value. And now how to get rid of these voids, because if we get the rid of voids then this digital elevation model will become very smooth, and then we can use for different analysis purposes. So one way which became popular is filling these voids or replacing these no data values using a coarser resolution digital elevation model like USGS DM. So if you overlay both of these and treat voids as a blank areas and read the values below from a coarser resolution DM and take that value as against these voids, then you end up with a digital elevation model which is now void free at 90 meter resolution, except the places where the voids might be a 1 kilometer resolution. So if you are not aware, you will not be noticing the correction here, but if you zoom this some certain parts, you may find this is 1 kilometer resolution which is suffering from seam. This is 1 kilometer resolution SRTM DM, and this is now corrected void free, and you can see that it looks much better and smoother. Of course, is a 90 meter resolution DM. Resolutions, there are 4 types of resolutions exist in remote sensing, and these are also influencing in GIS domain. One is spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. So these 4 resolutions, but mainly we are focusing in GIS is spatial resolution, which we have already discussed, that ability to distinguish close space object on an image. Spectral resolution is location, width and sensitivity of chosen lambda bands, or basically is a band width in a part of electromagnetic spectrum. So sometimes nowadays we are having hyperspectral bands, that means the bands have become very narrow, and therefore we go for we say it's a high spectral resolution data. In earlier remote sensing techniques like or sensors like Landsat MSS, we had relatively quite broad bands, and we say coarser spectral resolution. So number of bands have increased. Earlier sensors like Landsat MSS, we had only 4 bands. Now there are sensors available on board satellites which can acquire data at 512 or even 1024 bands, 256 bands for almost the same part of electromagnetic spectrum. So the width of each band is getting reduced. Even 1 micron size bands are nowadays available, but it depends again for what purpose you want to use that data. And the third type of resolution is temporal resolution. That means the time between observations when because satellites are orbiting, many satellites are not revisiting at the same time. Coarser the resolution, the revisit time would be much longer. And the coarser the resolution, revisit time would be shorter, whereas high spatial resolution would be going to be longer. So suppose there is a NOAA AVHRR. NOAA is a satellite, AVHRR is a sensor. So if we talk about NOAA AVHRR, revisit time is almost twice in a day, because it is having coarse resolution of about 1.1 kilometer. But if you talk say about Cartosat, then it revisit time might be after 22 days, because it covers a very small strip, and in order to cover the entire globe it takes time. So therefore temporal resolution varies with different satellites. Radiometric resolution, which is the precision of observation and not basically accuracy, that whether it is 6-bit data, 7-bit data, 8-bit data. Generally we nowadays most of the sensors are having 8-bit data, but there are sensors which are having more data, more width or radiometric resolution, like NOAA AVHRR is having 11 bits data. So if it is 8 bits data, which is quite common, standard one, then the values, the pixel values can vary between 0 to 255. That means total number of 256 values can be there. But if it is 7 bits, then you know that it would be, the values would be varying between 0 to 127. That means total number of values are going to be 128. And if it is a 6-bit data like IRS pen sensors, where there were 6 bits data, so the values were varying between 0 to 63, total number 64. So radiometric resolutions, and as time passing, the technology improving, we are improving almost everywhere except in maybe in temporal resolutions, because if we go for high spatial resolution, our temporal resolution, that means the revisit time of observations, becomes larger. So this is going in a reverse fashion. Otherwise spectral resolution is improving, spatial resolution is improving, and radiometric resolution is also improving. Now basically when we come to the remote sensing part here, because lot of data in GIS is coming from remote sensing, and that is why this component, this theory or this understanding need to be we have to spend some time to understand this one, and the resolution, because as I have said, the digital elevation models which are here now, these two digital elevation models have come from remote sensing sources. So how in remote sensing exactly which are the things which influences the spatial resolution, this we will see in detail. And as we have already seen that this is the availability, the examples are here, that you know that when you make a coarser resolution data, this is how the clarity disappears. And same with our photographs as well. Simple photographs, we can see that if you go for coarser resolution, nothing is basically visible there. Same with the satellite images. And also sometimes this is a issue that pixel size is not basically I mean means that it is not always that pixel size is like pixel size does not necessarily equate to the resolution, because nowadays the you know these resampling or subsampling techniques are available. So even the data has been collected, you can change the pixel size, but that does not mean that you are going to change the resolution. So this is what exactly here is. So when you go in a reverse way, like here you are doing a subsampling, that means like here input image is this, if you read alternate pixels, you may go for like this. So now you have gone for coarser resolution, again input image is this and you again read alternate pixels, you may end up something like this. So there are sampling, resampling and subsampling techniques are also available, but going backward is generally is not common, but people try to resample it to a smaller pixel size, sometimes to fit with other data sets. But that is not going to improve anyway the resolution of your data set. It will only repeat in both direction, x and y direction, one more value of the same input value of pixel. So that is why it is said that pixel size does not necessarily equate to the resolution. Now in case because a lot of data in in GIS is coming from remote sensing, so there are one important term here is, that is the IFOV, which is instantaneous field of view. So when data is collected, instantaneous field of view is basically a solid angle, and whereas the resolution which we assume is a square in shape. So when it is created, then those at the nadir view, at vertically just downward of the sensor, it is IFOV is perfect in order and as expected, as intended, but as you go away from the sensor and it becomes off nadir or oblique, then instead of getting a exact square, you start getting the rectangle, and then complication starts coming. But when an image is generated, then we always assume that your pixel or cell is representing a square area. So the IFOV, this is a solid angle, whereas on the ground we assume a square or rectangle, basically a square, and then associated. So that is why if your resolution is relatively low or coarser resolution image, then curvature of the earth will play a very important role, and on the edges these images which are covering a large area of the earth will have problems on the edges, and their resolution relatively the sharpness in those images will disappear relative or compares to the central part. And this example can be seen with NOAA AVHRR data, because the width or the swath of a one scene is about 2800 kilometer. So in the center of the image, your representation of the earth is truly in a square. Earth part is represented as a square, no issue, but when it goes on the side of the scene, that there the curvature of the earth plays very important role, and therefore you are covering a rectangular area which you are representing as a square area in an image, and therefore distortions are there, and the clarity of the image on the margins or at the border is not as good as in the center. So this ground resolution elements is equal to IFOV, and height. It depends on the height. Generally, these Earth orbiting satellites, whether Landsat, NOAA, Cartosat, almost all these satellites are orbiting around 940 kilometer plus minus 10 kilometers. So there you can consider height is almost constant, but if a very high resolution image is there, then IFOB angle is going to be very small, and therefore your ground resolution value is going to be distance or a area is going to be small, what we call as a higher spatial resolution. Here as a example is shown here, but when we go for a wide angle, and this is how it happens, but when we go for a very narrow, then we start seeing only a less distortions in the image, and other things will not come. This is in this is field of view, not in case of satellite images, but the concept why it is remains same. When you go in a photography, when you use the wide angle, then at the it is basically the area which is a curved area is being represented in a flat area, in a flat film or a photographic paper. But if you zoom it, then this curvature or this issue will not come. So that is why it is important to understand IFOB, height and the ground resolution which is concerned for us. Here also through this geometrical instantaneous field of view is constructed that in your sensor this is how it is there, but on the ground this is covering this much of the area. And now this is the last slide of this presentation is there is always a question that what the spatial resolution is appropriate for my area, and it is very hard to explain that depending on your project, depending on your requirements, one should choose appropriate spatial resolution. But what exactly that appropriate? There is a view graph or a figure was given by Schulz and Barrett in 1989 that for depending on different requirements or different projects, which satellite data or which spatial resolution data are good. So this is a resolution in time, this is the desirable area, where at that time it was in 89 it was assumed that this is the area where all these data will come. For example, if I say radar data, at that time radar data resolution was around 1000 meter, that means 1 kilometer. Similarly, that presently this NOAA series of satellite data is also having about 1.1 or that kind of resolution. So of course you can desire at a relatively high resolution, also resolution in time, that you desire images after even half an hour or each 12 hours would be there with a high resolution, and then you are having some other satellites like IRS now these or Landsat, now latest is Landsat 8 OLE series, and the resolution is definitely coming to about 30 meter or 15 meter here in this region. So this has shifted this much now, but repeat cycle the resolution in time, that is the temporal resolution, is still remaining there. So as I have already mentioned that higher the spatial resolution, lower is going to be the temporal resolution. The repeativity or revisit of the satellite is going to be much longer. Relatively coarser resolution, like in case of NOAA data, they may come after even every 12 hours, and therefore you may have coverage twice in a day with the relatively coarser resolution data, because their swath width, the area of coverage of the earth is much larger, and therefore the repeat cycle is much shorter. In case of high spatial resolution data, the swath width might be even 11 kilometer. So if I compare NOAA data, it is 2800 kilometer. With the high resolution data, maybe say 1 meter resolution data, the swath width may be 121 kilometer. So when the repeat cycle or repeativity or temporal resolution is going to be relatively very low when we compare with the NOAA data. So again, in the last I would like to mention, depending on your project, one must choose the appropriate spatial resolution of your data, whether it's a satellite data or it's a digital elevation model. But one thing one must understand before you employ such data sets in any of such projects, that what are the inherent errors or problems are associated with the data. Because as you know that error propagates in GIS. So we must know the errors which are already inherent errors, which are already errors in input data sets, whether it's a digital elevation model and your satellite data. Also mentioned earlier that we must also have the information about the data, that is the metadata. So if you are using say this Ester GDM, you must know that what is the accuracy of Ester GDM, how it has been acquired, and therefore you must record all those details with your project. Similarly, if you are using satellite data, say Landsat 8 data, then you must know that which date scene you have used, what was the resolution, which were the bands or spectral data, and all those details must be recorded, so that whenever this question of accuracy and time and any other details are asked, you must be able to answer those questions very accurately, depending on the having the information about the metadata. So thank you very much.